So when we're talking about inference, we know that we have this idea about what's expected versus what we obtained. And we're still making that comparison when we're looking at a regression analysis. Okay? Our targets here perform significance tests for the strength of a linear relationship. And we already have a way of measuring the strength with correlation. But we know that correlation does not imply causation. Now, we do have some tools for determining causation. Randomized experiment, and you have representative samples. If you get convincing results at the end of your hypothesis test, then you might be able to say that there is causation between the explanatory and the response variable. So now we can start to kind of entertain those in the same conversation if everything works out the way you need it to. We'll also be looking at a confidence interval. This will be a target in our next lesson. Not really getting into this today, but a measure that's very important when you're talking about linear models is the slope. Okay? The slope gives us that unit rate. It gives us the direction of the association. So we'll be talking about that critical value. And if we're using a sample to estimate something about the population, the slope can be the key value for that estimate. Now, some background again, when you're talking about a regression analysis, you're looking at a scatter plot for a representation of two quantitative variables. The explanatory variable is the x value, the response variable is the y value, and the method that we're using for regression is called least squares regression line that provides us with that line of best fit for your data set. Now, let's say that we have a scatter plot that looks something like that. We are interpreting the data that we have on this scatter plot as our sample. So we know that if we have a line of best fit for our data set, that this line of best fit is for the data that we have in front of us. But if that data is from a sample, then the implication is that there is a larger population of data out there. That if a linear model is truly what's happening here, maybe our linear model that we got isn't the perfect model for that population's data. So there is a population model that exists. Our data is a sample of that population model. And we want to know how accurate is our model for both the actual population model and predictions from our model. How accurate are they in relation to that population model? So we have some questions that we need to answer with this inference process. Is there really a linear relationship between x and y in the population? Or could the pattern that we see in the scatter plot plausibly just happen by chance? A big question that we've seen with our other tests of significance. Is the association that we have just due to chance alone? Or would that be incredibly unlikely to have happened if there were not some true relationship going on? Secondly, what is the slope that relates y to x in the population? Again, this idea about knowing something about the population from our sample, including a margin of error for our estimate of the slope. This kind of goes along with a confidence interval that I said we'll talk about on Monday. And lastly, if we use the least squares regression line to predict y for a given value of x, how accurate is our prediction? And again, the idea being a margin of error. So these are the questions that we hope to answer. Now, like we've seen in other sections, we have a single example that's going to serve as our walkthrough for this lesson. So our example problem in this lesson is that it's theorized that infants, newborn babies, who cry easily may be more easily stimulated than others, and that this easy stimulation is a sign of a higher IQ. So the idea here is that newborn babies that respond to the environment around them, okay, and the only way that newborn babies have to respond is to cry. So those babies that cry more are thought to have a higher IQ. And remember, we talked a little bit about IQ earlier in the year in relation to a normal distribution. IQ is thought of as a constant measure throughout your lifetime. That barring like a major catastrophic brain injury, that you essentially have the same IQ throughout your life. There's nothing you can really do to raise your IQ. And again, with a brain injury aside, there's nothing you can do to lower your IQ. So the way this experiment was conducted is that you have child development researchers exploring this relationship in the crying habits of infants between 4 and 10 days old, and their IQ that was measured later on when they were 3 years old. So 3 years old is about the very beginning of when you could start to measure a child's IQ. And that sort of an IQ test is not going to be the same type of test that you would give a young adult or an adult. Okay? But it is an initial measure of that sort of score. It may not be quite as accurate as a test that you would have later in life. So, the two variables that we have here. Explanatory variable is the number of crying incidents. Okay, they have it as count of crying peaks. And this is over this period of time that they measured. I can't remember if it was like a 24-hour span or 48-hour span, something like that. But the number of times that they cried, that is the X value, and the IQ at 3 years old is the Y value. So we see the scatter plot here in front of us. The raw data is in your textbook, and I'll show you that data set in a few minutes when we pull up the calculator. Now, from this scatter plot, we have the line of best fit drawn in there. And we're using correlation and regression to describe this linear relationship. We want to know if this observed linear relationship is statistically significant. Or does it just so happen that there is a mild linear relationship here that, again, no causation whatsoever. You're just seeing if this trend actually holds true. Now, when we look at the scatter plot, we can get some ideas about the form, the direction, the strength of the relationship, as well as like possible outliers and deviations. We're not really going to be talking about outliers in this unit. Looking at our data set, it appears like maybe this point right here, it seems to be a little bit further away from that expectation than other values, but it's not like completely inconsistent with our trend, and there's, as far as we know, no reason to exclude it from our data set. The word they use to describe this relationship is moderately strong. And I think that's a little bit generous here. And I would say maybe there's somewhat of a positive relationship. It is positive. It does look like there's a slight upward trend. I tend to think moderately is a little bit stronger of a word than exists here, but we'll look at the R value and we can make our own decision about what the appropriate description would be. As we said, there's no real extreme outliers here or potentially influential observations. So, to solve this regression analysis, again, a linear model for years, coming up through algebra, we're used to seeing a line in the form y equals mx plus b. And I mentioned this at the beginning of the year. In statistics, we don't really use this format of m for slope and b for y-intercept. Instead, we use our linear model as y equals a plus bx. And you'll see that it's important that we embrace this structure for our analysis here, because this is a sample. We put that hat on top of the y to indicate that this is based off of sample data. And we could potentially have multiple regression models supporting the population model that I've talked about. Now, the a value is the y-intercept. It's our initial value. The b value is the slope. Okay, so we're going to use this format for our interpretation here. And when you run the regression analysis, we find that we get an R value 0.455. Again, R value goes from -1 to +1. It tells you both the strength of the correlation and the direction. This is a positive correlation, so it's positive slope. If we're looking at a positive R value between 0 and 1, this is actually closer to 0 than it is to 1. So again, I don't think moderately is the best word. I would have maybe said there's somewhat of a positive correlation here. Make your own decision. But that R value, it is what it is. Here is our least squares regression line. As we said, y hat equals a plus bx. Should be an x on the other end there. We get an a value, a y-intercept of 91.27. Remember, for interpretation purposes, the y-intercept occurs when the x value is 0. So the implication here is that a baby that does not cry at all, based on our model, should have an IQ of about 91. The slope, we said, is important in our analysis because a lot of what's going on in the linear relationship is dictated by the slope. The slope of our model is 1.493, pretty much 1.5. And because that is a unit rate, for every 1 unit of x change, which means 1 more incident of crying, the IQ goes up by 1.5 points. That's what this relationship is saying here, and that's what's illustrated by the slope. Now, additionally, we have an R square value. We talked about what R square means. It is literally squaring this R value. But in this case, it corresponds with 0.207. Okay? R squared is about 21%, which means about 21% of the variation that we see can be explained by the crying. Okay? Only about 21% of the variation in this case can be explained by this model. So we have 79% of that variation. We saw that it wasn't by any means a perfect model here. 79% of this variation is unexplained. There are other factors that are contributing to it. So, is this observed relationship statistically significant? That is the question that we're trying to answer. Now, in order to use this regression model, okay, we have some conditions that need to be met, and this is where it starts to get a little bit complicated. As I said, we have a sample model, okay, y hat equals a plus bx. We are taking n number of these observations. This is representing a single observation from our data. But in theory, we have an infinite number of observations out there. And we want to be able to provide an idea of what that population's true model looks like. Our goal is to study or predict the behavior of y for given values of x. So when we do this, we have our sample value, okay? Intercept A and slope B. Those are sample statistics. We would like to know how they correspond with population parameters. We're going to call them beta and alpha. That's why we want to take on this format here. So the idea is that the population model that we're trying to describe, it looks like this. Mu sub y equals alpha plus beta x. You can think of this along the same lines as like population mean was mu, sample mean was x bar. This is sample, this is population. It's easier to connect that. A and alpha, B and beta. The Greek letters are used to represent the population values here. Now, we'll explain more about that model in just a second here, but for any fixed value of x, the response y varies according to a normal distribution. And these repeated y responses are independent of one another. What this means, we're using this model to make predictions. And the variability, the variation that we have between what we expect from our model and what we actually have in the population, that variation occurs in a normal distribution. And I have a diagram in our next slide to illustrate that a little bit. And all of these predictions are independent of one another. They have no influence. Okay? So whatever you get in one does not impact another. Now I do use a mu here to represent this end result for our population. I said that we have a bunch of possible theoretical samples. Okay? We could have one regression, y hat 1, y hat 2, y hat 3. For a given x value, and x is, we had a baby that cried 12 times, let's say. Using every possible model, the resulting y hat value when a baby cries 12 times, the average of all of those becomes the y value for our population model. That is the mean of all of those, okay, for that same x value. Okay? And that can be used to help contribute to the population alpha and beta values. Okay? Alpha and beta, they are unknown parameters. We've seen unknown parameters before. We didn't know population standard deviation, sigma. Okay? We didn't know the population mean, mu. So instead, we were allowed to use our, what are called unbiased estimators. Okay? And this is kind of getting into our next slide here. But instead of sigma, we used sample standard deviation before. Instead of mu, we used x bar. Okay? You use the sample data from what you have. Pretty much what we're going to be doing here. We have one more measure right here. We said that the distribution of these response variables y, it falls in order, falls on a normal distribution. Okay? Now, if it's normally distributed, there's a standard deviation, standard deviation that goes along with that. The standard deviation of y, we're going to call it sigma. It is the same for all values of x. So it doesn't matter if you're predicting this for 12 crying incidents or 20 crying incidents. The distribution of those y values is going to have the same standard deviation, is what this condition says. Now we don't know what that standard deviation is because it is a population parameter. There are 3 population parameters that we need to estimate: alpha, beta, and sigma. This is that distribution image that I mentioned a couple minutes ago. We are kind of taking an overhead view of our scatter plot. So here's the x-axis coming down here. There's the y-axis on the left side. This red line right here is our population regression line. Okay? That is the population model. You can see mu sub y equals alpha plus beta x. So this is truly what happens. When you have an x value, you substitute that into this model. This is what should happen for a y value. But across all of our regression models, y hat equals a plus bx, there's some variation with that resulting y. And that variation occurs in a normally distributed fashion. Okay? Sometimes it's higher, sometimes it's lower, but that distribution is normal. We have the same distribution, identical distribution for whatever x value we're estimating. And the standard deviation of this distribution is this sigma. Okay? It is the standard deviation of these y responses. I should pause. Any questions up to this point? Okay, so to estimate these population parameters, okay, we don't know them. Okay, what we can do is use our regression model. Okay, we have y hat equals a plus bx. We're going to use that sample slope, b. It is called the unbiased estimator of the population slope beta. So we can substitute that in to take its place. Same thing with the intercept a. That is going to be the unbiased estimator of the population intercept alpha. So we're going to substitute that in. The remaining parameter is sigma, this standard deviation. What we can do is look at what we predict from our model and what we got in our sample data and see how much variation there is between what we observed and what we expect. If you recall, we talked a little bit in chapter 5 about residuals. And the residuals help us find this standard deviation. A residual is the observed y value minus the predicted y value. So in this case, the y value, let's say we had a child who had an IQ of 110. But we would have predicted, based off of the number of times they cried, we would have predicted that they would have an IQ of 105. There's a residual of 5. It's 5 above what we would predict. In our sample data, we had 38 individuals. Some of them are going to be above the prediction. Some of them are going to be below the prediction. Okay? That's to be expected. And we talked about residual plots a little bit in the first semester. Let me flip screens for a second here to show you a little bit of what the calculator can do with residuals. We saw that GeoGebra does it pretty nicely. It's just another option that we can. We'll maybe take a look at that closer on Monday. But for right now, let's look at the calculator. So let me flip screens momentarily. So on the calculator, I have this data entered into L1 and L2. As I said, there were 38 individuals in here. Yeah? And you can see that, like our first individual, cried 10 times, corresponds 3 years later, has an IQ of 87. 12, 97, 9, 103, and so forth. The table is in your textbook if you want to look at that. Now, we can let the calculator find the residuals for us. Okay, we'll go over to blank list 3 here, and up in the margin, I should say this is only an option after you do a regression analysis. So if you do stat and then calculate, and you could do the familiar AX plus B or the more statistical, what we want, number 8, linear regression. We can put our regression equation into Y1, that's a good idea. Vars function Y1, down to calculate. Here's our regression model. Here are the values that we've already seen up to this point. Y-intercept of 91, slope of 1.49. There's our R squared. We talked about 21% of the variation can be explained by this model, and the R value of 0.45. Pretty weak, in my opinion. Now that we have that, go back to the stat and the lists. And in list 3, we're going to go up into the heading, and we're going to press second and the stat button, which brings up list. And you'll now see option 7 is residual. It will create the residuals. It will do observed minus expected for us for every one of those 38. Okay? So we're telling it to do this in list 3, and there they are. So we haven't even looked at the regression equation, but in list 3, this baby cried 10 times, has an IQ of 87. Well, it turns out that's 19 points lower than what we would have predicted from our model based off of this data. 12 crying incidents, 97 was the IQ, that's 12 points lower. Some of them are higher. Down here we have a 12 crying incidents. That baby had an IQ of 119. That was 9.8 IQ points above what we expected. Those are the residuals. And we looked at a residual plot. We can make a residual plot somewhat easily now as a stat plot in our graphing calculator. Rather than do our original scatter plot and compare list 1 and list 2, we're still going to use our x values from list 1, but now our y values will be list 3, the residuals. So let's go second, stat plot, and just verify that we want a scatter plot. We want L3 as our y list, so second, and then the number 3 to get list 3 looking there, or going there. And then we're going to do zoom number 9. Zoom stat gives us a good window based off of the statistics we have in our lists. And here is our residual plot. Essentially what a residual plot does is it rotates the scatter plot so that the line of best fit is now the x-axis. And a residual, we know, is how far above or below what you expected to have happen. It's modeled on our plot now. So this point up here, that's our outlier, or suspected outlier that we thought. It was the furthest away from what we predicted from our model. With the residuals, the mean of all of the residuals is 0. Some are above, some are below. They average out to 0. So what you can determine from the residual plot is, like, what are really good predictors? Some of these points are pretty close to the x-axis. Ideally, if you have a really strong correlation, you have all of your points pretty close to the x-axis there. But what you're looking at to confirm a linear relationship is that you have kind of a random dispersion of these residuals. That there's no identifiable pattern for them. Like if you saw like a parabola type shape a linear model is not a good predictor in that case, okay? Which we're not going to get into nonlinear models, but in this case, this is random enough. So despite our relatively small R value, a linear model is still appropriate in this case. What we want to know is that linear model, is it just by chance? Or does this actually have a relationship that is kind of proven, that is causing? Okay? Are these crying incidents an indicator that the IQ is higher or lower because of their relationship, their reaction with the environment around them? Any questions on the residuals? We'll do more with the calculator coming up here. Let's go back. All right, so anyway, we were talking about standard error. The regression standard error uses these residuals. Now, this is an equation that I don't even know why it's here, okay? You're not going to do this by hand, okay? You would not want to do this by hand, but you are finding this regression standard error by taking each residual, okay? Each individual residual, like Dr. Seuss's interpretation of statistics. So you take each individual residual, square it, and then add them all together, multiply by 1 over n minus 2. That's to account for the degrees of freedom here. You have two variables, so the minus 2 is what you have. Let's take the square root. That is your regression standard error. And you're going to use this S, this standard error, to serve the purpose of that population standard deviation, okay, for the Y values. Okay, so when you use the technology, as I said, we've kind of reached the limit with GeoGebra, but some of these other outputs that we'll see, a lot of our problems, as you saw with their homework assignment that's due tomorrow, they have an output here that's easy to understand if you know what is provided. Here's our regression equation right there. This is from Minitab. 91.3 plus 1.45 times the cry count, which is the X value. We'll talk about the t-score and the p-value on Monday, but we have an R-square value of about 21%. We've talked about that. This is that standard error calculation for our values. 17.5 in this case. Our regression model, we talked about the intercept, we talked about the interpretation of the slope as a unit rate, 1.5 essentially. With the calculator and Excel, okay, these are the two that we have. We'll take a quick look at Excel on Monday, get that statistics package loaded for us. With the graphing calculator, let me flip screens one more time before we wrap up for the end of the day. Okay, so on the calculator, we're going to press Stat and over to Tests. And of all of our tests, we're going to jump down to the bottom. Past chi-squared give this a fit. Talk F-test later. Linear regression t-test and linear regression t-interval. Now, for right now, we don't know what the t-test involves. We haven't talked hypotheses or anything yet. But as a result of performing this test, the calculator will provide us with this standard deviation. So if we make that selection, confirming that we have our data in L1 and L2, okay, you don't use the residuals in this case. Alternative hypothesis, we'll just leave it as not equal to for right now. This is optional here, putting that regression equation into Y1. Hit enter. All right, here's our linear model. We have the t-score and the p-value right there. Degrees of freedom, we'll talk about those on Monday. This does a regression analysis for you. So there is the A value for intercept, the B value for the slope. Here is that standard deviation that we just saw, the standard error. 17.5 essentially is our approximation for the standard deviation of the distribution of those y values. R square and R are also provided as part of this analysis. All right. Any questions up to this point? This can be pretty complicated, but it kind of gives you an idea. The big idea is here that our regression model is a sample value for a bunch of other possible models that all explain, in theory, what is a population model that describes what's truly going on in the population of all possible samples. We want to know and be able to answer the question, the relationship that we see in our model, does it explain a true relationship in the population? And we'll pick up with that for our lesson next time.